Sometimes we find this expression is still not simple enough. In practical applications, the doping on the two sides of the p-n junction are usually asymmetrical. It is because a p-n junction is usually obtained by counter-doping one type of material to convert part of it to the opposite type. The counter-doping is usually done with much higher doping concentrations than the existing dopants to minimize the impact of the background dopants. Some typical doping concentration of the lightly doped side is around 10 to the power 15 to 16, while the heavily doped side is around 10 to the power 18 to 19 per cubic centimeter. With these numbers in mind, Na and Nd is usually differ from each other by more than 1,000 times. If you look at the expressions for the depletion region width, the higher doping concentration term can be removed, and the depletion region width is mainly controlled by the doping concentration of the lightly doped side. Graphically, a p-n junction is usually one-sided. For example, a p plus n junction will have charge distribution looks like this figure. We commonly use the plus sign to represent heavy doping. And the expressions for the depletion region width can be approximated by the one given here. The only variable is the doping concentration of the lightly doped side. And therefore, once the doping concentration is given, both the built-in potential and the depletion region width can be found. So, up to now, you should remember that the properties of a p-n junction are mostly controlled by the lightly doped side. Visually, the physical and Venn diagram representation of an asymmetric p-n junction is shown in the diagram here. The built-in potential and the depletion region width can be calculated by the expressions given here.